The idea of black holes has fascinated physicists for more than a century. It began to gain popularity in 1916. These cosmic anomalies, which sit at the nexus of enormous gravitational forces and a strange invisibility to our knowledge, are among the most fascinating and mysterious things we are aware of. A black hole is still an unknown entity in the universe, with a mass that could be up to 2 to 4 million times that of our Sun. Our knowledge has grown from virtually nothing to assembling more details after decades of intensive investigation, with even more findings being produced recently. An innovation by M. Kaku has made shocking discoveries regarding the innards of black holes that could contradict our long-held beliefs and provide fresh insights into the characteristics of these celestial bodies. Deeper investigations into what may have been disregarded up to now are made possible by this new information. Come along with us as we delve deeper into the intriguing realm of black holes and discover what lies beyond the expansive and motivating universe. But it's important to review the fundamentals of black holes before delving into Kaku's most recent discoveries. Even while the most of us are at least vaguely aware of what a black hole is, several important details are still unknown. Black holes were predicted by Albert Einstein's revolutionary general relativity theory in 1916. The idea was only theoretical at the time, and proof that black holes are actual things in space wasn't found until roughly 50 years later. This discovery was made in the 1960s while researching the star X1, a bright celestial body that emits X-rays. Observations revealed that these X-rays were being pulled into a dense, unseen mass rather than traveling randomly. Our understanding of the universe was altered by this mass, which was eventually determined to be a black hole. The finding was significant because it demonstrated that black holes were real, elusive objects that needed more research rather than being the stuff of Einstein's dreams. Scientists from all across the world started a global mission to learn more about black holes after this revolutionary discovery. Through their work, it was discovered that the Milky Way alone might contain up to 100 million black holes. Albeit this estimate is still speculative because of the difficulties in identifying them. Understanding black holes is even more important since, despite their extreme difficulty in being located, scientists estimate that millions of these enormous objects are concealed within our galaxy. Let's simplify the fundamental idea of gravity. Anything that enters a black hole's domain gets compressed into a singularity, where the laws of physics as we know them stop working due to the enormous gravitational forces that black holes exert. To put it another way, black holes are like enormous vacuum cleaners that draw everything in. A person falling into a black hole will eventually stretch out and become a singularity, their body ripped apart by the powerful gravitational pull before the point of complete destruction. This is one of the most scary parts of studying black holes. Although they can be found all across the cosmos, it is recommended to stay away from them. Even though the closest black hole is some 500 light-years away, the closeness nevertheless causes serious worries. The first clear photograph of a black hole, the M87 black hole, was captured by scientists in 2021, marking a significant milestone. This accomplishment was the product of many late hours spent shooting pictures and arranging them to form a single, coherent picture. As additional information became available, scientists discovered that, in contrast to the popular belief that black holes are simply limitless voids, they actually have 3 separate layers. The event horizon, which denotes the point beyond which nothing may escape, is the first of these layers. Anything that crosses this line will unavoidably be pulled toward the direction of the black hole. Light itself becomes caught in the second layer, referred to as the photon sphere, where strong gravity forces prevent it from escaping. Last but not least is the singularity, where all matter is condensed into an incredibly tiny point, where the fundamental foundation of reality crumbles and all of the established laws of physics vanish. Even more fascinating is the fact that every black hole is distinct from the others. Despite adhering to the overall 3-layer structure, they might act rather differently. This makes them especially difficult to investigate because black holes cannot be studied using standard scientific techniques. Scientists are forced to look into these abnormalities indirectly, either examining the gas and dust swirling around them, or by studying the radiation they release. Since anything that crosses the event horizon is inexorably drawn toward the singularity, where it is crushed into nothingness, sending a probe straight into a black hole is a pointless endeavor. Because of this inevitable outcome, Billions of dollars cannot be spent on probes that would fail before providing any useful information. As a result, even though black holes are three-dimensional singularities, physicists are forced to investigate them in two dimensions. The fact that no two black holes are alike makes studying them even more difficult. We have to take into consideration the disintegration of conventional physics when examining them. Black holes may arise when enormous stars collapse in on themselves. According to theories about their beginnings, a star eventually collapses into a black hole as its fuel runs out, and it is unable to generate enough energy to resist gravity's inward pull. This process keeps going until the compressing matter turns into a singularity if the star is large enough. NASA researchers focused on the M87 galaxy, which is located near the heart of the universe. There, they saw a strong vortex of hydrogen gas whirling at an incredible 1.2 million miles per hour. This gas should have been blown apart by the centrifugal force, but it stayed together, indicating that there is a large object, likely a black hole, at the core. It is estimated that this object has a mass up to 3 billion times that of the Sun. The New Zealand mathematician Royer put forth another important idea in 1963, explaining the behavior of revolving black holes using Einstein's equations. He maintained that a revolving black hole creates a narrow ring-like structure called the ergosphere, instead of collapsing into a point, as was previously believed. Understanding how physics principles break down around black holes depends on this revolving disk of substance. An Einstein-Rosen bridge, a hypothetical wormhole that would offer a shortcut through space-time, linking far-flung parts of the cosmos or perhaps parallel universes, was also predicted by Royer's model. Understanding Michio Kaku's astounding explanation is crucial to understanding the concept of a wormhole. According to the theory of Einstein, space-time is a four-dimensional fabric that is distorted by mass-containing objects. Gravitational fields produced by this warping affect how other things move. Imagine space-time as a sheet of paper. If you fold the paper, you can make a shortcut from one place to another. The essence of a wormhole is this shortcut, a space-time route that might virtually instantly connect far-flung locales. Wormholes are a natural byproduct of general relativity, despite the fact that they are a theoretical idea and that there is no concrete evidence for them. Wormholes, however, would collapse rapidly if they were formed since they are naturally unstable. Despite this, physicists have long been fascinated by the notion that a wormhole could serve as a portal to other regions of the universe or even to distant eras. The CR wormhole, which bears Royer's name, is one particular kind of wormhole that has generated interest. Theoretically, two far locations in space, time could be connected by this hypothetical wormhole, perhaps tying together distinct timelines or worlds, with the possibility of ground-breaking findings that might fundamentally alter our knowledge of the cosmos. Scientists are still enthralled with the quest to comprehend the nature of black holes, wormholes, and the structure of space-time. The increasing interest in gravitational wave astronomy is one of the most intriguing advances in the study of black holes as we continue to explore the cosmos. Following the groundbreaking discovery of gravitational waves in 2015, which validated one of Einstein's predictions from more than a century ago, this discipline came into being. When huge objects accelerate, like when black holes collide and merge, they create ripples in space, time known as gravitational waves. Studying the most extreme cosmic phenomena has become possible because to the ability to detect these waves, scientists anticipate gaining greater in-depth knowledge of black hole mergers, neutron-star collisions, and other events that were previously outside the scope of conventional telescopes as new observatories are constructed and existing technology advances. Instead than depending on electromagnetic radiation like light, gravitational wave detection enables direct observation of black hole interactions through space-time distortions, making it unique. Since black holes themselves don't emit light or any other type of electromagnetic radiation, this method is very helpful. Because of this, they are frequently concealed from traditional observation techniques. These elusive objects can be studied using gravitational waves, which give information on their masses, spins, and the circumstances that led to their genesis. Scientists are using this new observational tool to assist them answer concerns regarding the basic behavior of black holes and the harsh conditions that surround them. The development of telescope technology has also greatly enhanced our capacity to investigate black holes in addition to gravitational waves. One of the most innovative instances of how a combination of worldwide resources can yield ground Breaking outcomes is the Event Horizon Telescope (EHT). In 2019, the EHT obtained the first ever image of a black hole at the heart of the M87 galaxy by connecting radio telescopes from all across the world. This momentous accomplishment made it possible for researchers to see a black hole's shadow, adding to the expanding corpus of knowledge about them and offering tangible proof of their existence. Future pictures will probably show considerably more information about the composition and activity of black holes as telescope technology like the EHT develops, possibly providing insight into their function in the birth and evolution of galaxies. There is a lot of promise for black hole research in the future. Our knowledge of these mysterious things will continue to grow as new observational methods are developed, such as the investigation of gravitational waves and improvements in imaging capabilities. Further understanding of the nature of space, time itself is also anticipated as a result of the search for unified theories like superstring theory and quantum gravity. We might learn more about the basic forces governing the universe as we solve the mysteries surrounding black holes, which could lead to fresh insights into everything from dark matter to the very structure of existence. The study of Hawking radiation, a theoretical prediction made by physicist Stephen Hawking in the 1970s, is another exciting area of black hole research. His hypothesis states that quantum phenomena close to the event horizon cause black holes to release radiation rather than being completely black. According to this phenomena, which is now called Hawking radiation, black holes may eventually evaporate as a result of losing mass and energy over time. Even though this radiation hasn't been found yet, its effects could fundamentally change how we think about black hole physics. Our present theories of black hole life cycles may be called into question if Hawking radiation is verified, which would indicate that black holes are dynamic things that change over time rather than fixed structures. There is still a lot of interest in the nature of black hole mergers. As was previously noted, gravitational waves are produced when two black holes collide, and these waves travel through space-time. There are a lot of unknowns in the process itself, though. For example, researchers continue to study the dynamics of the surrounding space, time during these catastrophic events, the interactions between the merging black holes, and the effects of their mass and spin on the final result. In addition to learning more about the behavior of these objects, scientists are also learning more about the fundamental nature of gravity and the structure of space-time by examining the signals generated by black hole mergers. Another topic of continuous study is the function of black holes in the larger structure of galaxies. It is generally accepted that supermassive black holes are found at the core of many huge galaxies, including our own Milky Way. The evolution of their host galaxies may be significantly impacted by these black holes. For example, star formation rates, as well as the general structure and dynamics of galaxies, can be influenced by the energy and radiation released by material falling into supermassive black holes. Gaining knowledge about the interaction between black holes and the galaxies they reside in may help us better understand how galaxies grow, change, and eventually perish. Furthermore, fascinating hints regarding the principles underlying their growth and energy output are being revealed by the continuous research of black hole spin. The rotation of black holes, which is known to occur at extraordinarily high speeds, is crucial to their interactions with their environment. According to theoretical models, a black hole's spin may have an impact on the development of relativistic jets, which are streams of high-energy particles that emerge from the hole's poles. These jets have the ability to travel great distances, sometimes even larger than the entire galaxy. Scientists aim to learn more about the processes that take place close to the event horizon and how they contribute to the cosmic phenomena surrounding black holes by studying these jets. In conclusion, research on black holes is still developing quickly, with new findings and innovations being made on a regular basis. Scientists are gradually solving the puzzle of these intriguing celestial objects as new theories and technological advancements are developed. We are getting closer to solving some of the universe's most profound mysteries, whether it is through the discovery of gravitational waves, improvements in imaging methods, or discoveries in theoretical physics.